Good morning, class. Today we're going to take a look at our first free body diagrams. So first, let me just remind you that what is a free body diagram? Okay, a free body diagram is a representation of all the forces that are acting on a particular object. And really where those forces are going to be applied are in actuality where they're being applied on the object. But to simplify things at first, we're going to be looking at the center of mass of the object as if all the forces were acting at the center of the mass. And we'll be drawing those forces as if they were all acting from the center of the mass out. In other words, the way that the force acting on the object would cause the object to move. So just to reiterate, okay, all the forces that are acting on an object, in this case we're going to draw a first free body diagram on the book, are vectors. So that indicates the magnitude and direction of the force. So the length of the vector arrow is going to be the magnitude of the force, and the direction of the vector arrow itself will show the direction. And you're going to want to try and keep these things in scale. So let's draw a free body diagram of this book that is resting here by itself. Okay, so we're going to look at our free body diagram right here. And you can see we have the book resting on the table. And we have the first force is the force of gravity, which is pulling straight down on it. The dot is representative of the center of mass of the object, okay, in this case the book. And therefore we're drawing the force of gravity pulling straight down on the object. And then there's a normal force. In actuality, the table is pushing back with an equal and opposite force, in this particular case, supporting the book. Otherwise, the book would be accelerating down towards the center of the earth. So these length of these arrows, since the book is not accelerating, okay, we know that the force normal in this particular case is equal to the force of gravity. So the force of gravity, we actually have an equation for that. It's always going to be the mass of the object in kilograms times the acceleration due to gravity, which we know is g. This is why before, when we made a big point about g is a positive 9.8. Be careful not to put in the negative 9.8 that we were using for free fall, in which case it was negative g when we put our frame of reference for the vertical position of the acceleration. This is g, which is 9.8, positive 9.8 meters per second squared. This force of gravity is also the weight. So the force of gravity of every object here on Earth is the weight of the object. It's the mass in kilograms times the acceleration due to gravity, little g, or 9.8 meters per second squared. We also have the force normal, or normal force, as it's also referred to. F sub n is going to signify the normal force. This is always a pushing force. Okay, it's never a pull. The normal force is a support force that is a support push from a stable body object. Right now, I'm standing on the floor, and the floor is supporting my force of gravity, or my weight, by pushing back up on my feet. In actuality, the whole surface of this book is being supported by the table. It's providing a normal force. Now, as I lean or push against this wall, the wall is also pushing back with an equal and opposite force. It's supporting me. So as I push, it's able to push back with a normal force perpendicular to this surface. If it wasn't able to respond with that reaction force and push back and stabilize that force that I'm applying, then we would have a wall that would be knocked over. So it doesn't have to be, a normal force does not always have to be from the ground or from the table. It is also not always equal to the force of gravity. So be careful. In many of the examples that we do, it is often equal to the force of gravity. But that's only really for the specific examples. As we progress and get more complicated problems, you'll see that that is not the case. So be careful. The force normal is not equal to the force of gravity. It is, however, a support force from a stable body. Now, if we're just letting it sit here, this is in fact our free body diagram. However, if I push with a force applied, like so, I'm adding some horizontal forces. These are all vertical forces. So as I push, we call that an applied force. There is also friction that is occurring between the book and the table as I push it, looking to accelerate the book. So let's go and add these forces to our free body diagram. So we've added the force applied, me pushing the book to your right, and the force of friction that's opposing it. Now, notice that the force applied is larger in length or magnitude of the force applied than the force of friction, excuse me. If both the force applied and the force of friction were the same, that's what it would look like. If they're canceling each other out, there is no actual change or movement or acceleration. So in this case, the force applied is larger than the force of friction, which is why you see the book accelerating. Okay? Now, something to think about. The force applied, or the applied force, F sub A, is always, it's really any force that can be applied to an object outside of the object itself, outside of its system. So any force that's applied to an object, it's kind of a catch-all, okay? But any force that gets applied, there's various ways that it gets applied. Generally speaking, it's a push. It can be a pull though, but oftentimes with a pull, it will become a tension force, and we'll talk about that in a second. The force of friction. The force of friction is capital F sub F, okay? It's going to be opposing the direction of motion. So in this case, the book is sliding to your right. The frictional force wants to oppose it. And we know this just from our own experiences in everyday life, that typically friction is always fighting you. In some cases, friction is actually your friend, and we'll talk more about that later. Parallel to the contact surfaces. So right now, the book is in contact with this table, and they are parallel with each other, and they're rubbing and sliding against each other. So the direction of the frictional force, when you have two objects in contact rubbing with against each other, is going to be parallel to that surface. In this case, parallel with the table. So it's going to be in this negative x direction. So this is our first free body diagram of a book being pushed in this direction here. And it covers all the things we talked about. Let's take a look at another case. But before we do that, I just want to point out one thing, that ultimately to find the acceleration of this book, which we'll do in another example, we're using Newton's second law. Again, Newton's second law is the summation of the forces is equal to the mass times acceleration, where both the net force, notice that there are multiple forces involved here, but the net force will cause this mass to accelerate, where both force and mass are vectors. All right, let's take a look at another example. Okay, in our second example here, we have a metal sphere that is suspended or hanging from a string. Let's look at the free body diagram for this metal sphere. Okay, so our free body diagram of the hanging mass here, this sphere, it really only has two forces acting on it. Still the force of gravity, which is pulling it straight down, and the force of tension. There is tension in this string that is actually pulling up on the mass, opposing the force of gravity. They are equal and opposite to each other, which is why the hanging sphere is not moving and it's not accelerating. So I know that these forces are actually canceling each other out. Now, this tension force, okay, is really along this string. There is equal and opposite forces. So the string is pulling up on this mass. So that's why this is in the free body diagram. If I were to extend this free body diagram to also look at this arm here coming off of this stand, it would look something like this. Now, this force of tension in the string that's pulling up on the mass is the same force of tension that is pulling down on this lever arm that is hanging out off of this stand here. So anytime that there's a rope, we have equal and opposite forces acting on each other on either end of the rope. And it is a pulling force, so it's pulling up on the ball and it's pulling down on this arm. So it's whether it's a string, a rope, a chain, there is a pulling action involved, often is referred to as a tension force. And that tension is in the string itself. But when you're drawing a free body diagram of just the object, you look at it from the object's perspective. So from the metal sphere, I don't really care about what's going on outside of here for this moment. I'm just drawing a free body diagram from the perspective of the sphere in this case, which would mean that I only need to include this force of tension that is coming off of here. I'm simply adding this extra diagram up in here to show you that this string that's connecting is an equal and opposite. These two forces of tension are equal to each other. And we'll learn more about force tension in another lesson as well, but I just wanted to point that out to you. Okay, let's take a look at our last example of a free body diagram. Okay, so we have the same book from the first example, except now we're on an incline on a plane. So let's take a look at how this free body diagram works given this scenario. Okay, so when we're looking at this free body diagram, we can always start with our force of gravity. It's going to help us. We always know that the force of gravity is acting on these objects, and the direction of the force of gravity is always going to be straight down towards the center of the earth. The fact that this book is on an incline doesn't change the fact that gravity is pulling straight down on it. Now, the inclined plane is supporting pushing back on the book with a normal force, or the force normal, okay? So we know that it's always perpendicular to the surface. Something I wanted to add earlier. So that's actually a perpendicular. Forgot to mention that earlier. It is a perpendicular support. So it is 90 degrees relative to the inclined plane, even though the force of gravity is straight down. Now, I drew on here the force of friction because if it wasn't for friction, there is a portion of the force of gravity that is actually pulling the book down the inclined plane. Now, I'm going to draw this out in dotted lines to show you the different vectors of the force of gravity so that you can see and visualize what it is I'm talking about. So there is a parallel component of the force of gravity. These are the two components of the force of gravity with respect to the inclined plane. Now, there is an angle here that is being created. The angle of the incline, which is down here relative to the table, and here's the inclined plane. So this is where we have to really be careful, and we have to be careful about how we're analyzing these vectors. We'll have a separate lesson specifically on this, but I first just wanted to show you to get you introduced to it. These components are not in there. If we just look at the actual free body diagram, it is the force of gravity, the force of friction, and the force normal. This force of friction, because we know it is parallel to the surfaces that are in contact with each other, which is the inclined plane in the book, and the parallel force of gravity wants to slide this down the inclined plane, I know that the force of friction wants to oppose the direction of motion, and I know that it is parallel to the surface, therefore it is up the inclined plane. That is, the force of friction is actually pulling it up the inclined plane, or opposing its motion to prevent it from sliding down. I also drew this the same length as this force of gravity parallel because, in fact, the book is not accelerating in any direction. So all the forces must cancel out when we look at Newton's second law. So this is an example of all the free body diagrams, the book at rest, laying flat and horizontal on the table, the metal sphere that was hanging, where we got a little bit of an introduction to the force of tension and the force of gravity, and here we have an inclined plane example with the book still at rest on the inclined plane. Thank you, and I'll see you soon.